Have you ever paused to wonder how your body performs that incredible feat of converting, the food you just ate into the raw energy powering your muscles?
It's a fundamental biological process, right?
Yep.
And the chemistry behind it, well, it dives deep into a really fascinating corner of organic chemistry.
Yeah, and it's not just theory. It's the foundation for designing new drugs, building complex molecules. And, as we'll see, it's crucial for life itself.
Welcome to the deep dive. We take complex information, distill it down, and hopefully give you a shortcut to being truly well-informed.
Today, we're cracking open a really key chapter, alpha carbon chemistry, enols and enolates from David Klein's Organic Chemistry.
Our mission today is clear. Explain the key concepts, the mechanisms behind these powerful reactions, and the sort of problem-solving techniques that make this chemistry so versatile and useful.
We're going to explore a whole suite of reactions that let chemists form carbon bonds, basically building molecules piece by piece.
Exactly. It's like a toolkit for synthetic chemists, offering incredible precision.
So, get ready to expand your understanding of chemical synthesis. We'll touch on practical applications and some surprising connections. Let's unpack this.
All right, so our journey begins with the star of the show, the alpha carbon.
Okay.
In organic chemistry, when you have a carbonyl group that's C, double bond, O, we use Greek letters, right, to map out the neighbors.
Alpha, beta, gamma.
Exactly. The carbon atom, or atoms, sitting right next to that carbonyl, those are the alpha carbons. The next ones out are beta, then gamma, and so on.
So what's the big deal about the hydrogens attached to these alpha carbons? Why are they the key players here?
Because those alpha protons, as we call them, are surprisingly acidic, much more than typical CH bonds.
Ah, okay, so they can be removed.
Precisely. They can be plucked off. And that allows the alpha carbon to transform into this highly reactive hotspot. And this reactivity shows up mainly in two forms, enols and enolates.
Let's start with enols then. What exactly is an enol?
An enol is what we call a tautomer of a ketone or an aldehyde.
Tautomer.
Think of tautomers as constitutional isomers that rapidly interconvert. Same atoms, just arranged differently specifically. The position of a proton in a double bond shifts.
And crucially, they are not resonance structures, right? Because atoms actually move.
Exactly right. Atoms move, not just electrons. Now, typically, the ketone or aldehyde form is overwhelmingly favored in this equilibrium.
Like massively favored.
Oh, yeah. For cyclohexanone, for instance, it's over 99.99% ketone. So you might think enols are just these fleeting ghosts, too unstable to be really useful.
There's always a but in chemistry.
There often is. And here's where it gets really interesting. Some enols are stable enough to hang around in significant amounts.
Why? What makes them stable?
Well, take beta-diketones, like 2,4-pentanedione. The enol form can be anywhere from 70 to 90% of the mixture.
Wow, that's a huge difference.
It is. And this stability comes down to two main things. First, a conjugated pi system. The double bonds line up, letting electrons spread out, which lowers the energy. Think of it like a superhighway for charge.
Makes it more stable, happier.
Exactly. And second, intramolecular hydrogen bonding. The enol's OH group forms a hydrogen bond with a nearby carbonyl oxygen. It's like the molecule is hugging itself into this stable six-membered ring.
Neat. And you mentioned phenol earlier as an extreme example.
Right. Phenol's technically an enol, but it's part of an aromatic ring. That aromaticity makes it incredibly stable, so the ketone form is basically non-existent.
So whether formed in acid or base, the alpha position of an enol is electron-rich, making it nucleophilic. Ready to attack stuff.
That's the key takeaway. It's a nucleophile. But while enols are reactive, enolates are the true powerhouses here.
Okay, enolates. How do they form?
If you treat a ketone or aldehyde with a strong base, you completely remove that acidic alpha proton. What you're left with is a negatively charged species, the enolate, and it's resonance stabilized.
Resonance stabilized, meaning the negative charge isn't stuck on the carbon?
Correct. It's shared between the alpha carbon and the oxygen atom. This stabilization is key.
And you called them ambident nucleophiles, meaning they can attack from two places.
Yep. Ambident, two teeth. The oxygen can act as a nucleophile, or the alpha carbon can. For most of the reactions we care about today, it's the carbon attack that forms new carbon-carbon bonds, which is often what we want in synthesis.
So compared to enols, enolates are just stronger.
Much more reactive,
Yeah.
because they have that full negative charge. And unlike enols, which are usually just transient intermediates, enolates can actually be prepared and, hang around long enough to be used deliberately in reactions. They're incredibly useful building blocks.
Okay, this brings up a crucial point. Choosing the right base. You said a strong base for enolates. Why does it matter so much?
It matters a lot. Aldehydes and ketones, their alpha protons typically have pK values around 16 to 20. That's roughly similar to alcohols.
Okay.
So if you use a milder base, like an alkoxide ion, say, sodium methoxide, you only set up an equilibrium. You'll have some starting ketones, some base, some enolates, some alcohol. It's a mix.
And that's bad.
It can be very problematic
Mm-hmm.
because the enolate you just formed is a nucleophile, and the starting ketone still floating around is an electrophile. They can react with each other in unwanted ways, like self-L reactions we'll see later. Messy stuff.
Ah, I see. So you need something stronger to avoid that equilibrium mess.
Exactly. That's where strong non-nucleophilic bases come in. Think sodium hydride, ANH, or, very commonly, lithium disopropylamide, LDA.
LDA. Hear that one a lot.
You do. These bases react irreversibly and completely convert the ketone or aldehyde into its enolate. NaH generates hydrogen gas, which bubbles away, driving the reaction forward. With LDA, the deprotonation is just complete. Only the enolate is present.
Clean. No starting material left to cause trouble.
Precisely. It avoids those equilibrium issues and side reactions.
And what about those beta-diketones you mentioned earlier, the ones with stable enols?
Ah, yes. They're a special case. Their alpha protons are way more acidic, with pK values around 9. That's about 1,000,000 times more acidic than a regular ketone.
Wow. Why so acidic?
Because the enolate they form is doubly stabilized. That negative charge gets spread over 2 oxygen atoms and the carbon in between through resonance.
So it's super stable.
Extremely stable, which means you don't even need a super strong base like LDA. Even mild bases like hydroxide or alkoxides can completely deprotonate them to form the enolate quantitatively.
So understand the PICO and choosing the right base.
Ah.
Fundamental stuff.
Absolutely critical for controlling these reactions.
Okay, let's move on to actually using these enols and enolates. How about alpha halogenation? Putting a halogen on that alpha spot.
Right. Under acidic conditions, ketones and aldehydes react with halogens, chlorine, bromine, iodine at the alpha carbon.
What's the mechanism look like?
It actually goes via the enol. First, the carbonyl oxygen gets protonated by the acid. Then a base, like water, removes an alpha proton to form the enol intermediate.
The enol we talked about earlier.
That's the one. And this enol formation is usually the slow, rate-determining step. That's why the reaction rate doesn't depend on how much halogen you add, which is kind of interesting.
Huh. So the enol forms slowly, then reacts fast.
Exactly. The enol, being nucleophilic at the alpha carbon, then attacks the halogen molecule, like Br2. Finally, another base removes a proton to give you the alpha halogenated product.
And you mentioned something about autocatalysis.
Yeah, a neat little detail. If you use bromine, the reaction produces HBr as a byproduct. That HBr is an acid, so it actually catalyzes the reaction further, speeding it up as it goes along.
Clever. What happens if the ketone isn't symmetrical, if it has 2 different alpha carbons?
Good question. That's a common challenge. Halogenation tends to happen mainly at the more substituted alpha carbon,
Why there?
because that position forms the more stable enol intermediate. Remember, more substituted double bonds are generally more stable. So you often get a mixture, but favoring the more substituted side.
Okay. And these alpha haloketones can be used for other things.
Yeah, one common follow-up is to treat them with a base. This can cause an elimination reaction, kicking out HX and forming a double bond between the alpha and beta carbons. That gives you an apogo-unsaturated carbonyl, though sometimes yields aren't great.
Right. Now, what about carboxylic acids? You said they don't enolize easily.
They don't. So standard acid-catalyzed halogenation doesn't work well. For them, we have a specific named reaction, the Helvell-Hordzinski reaction, or HVZ.
HVZ. Got it.
This uses bromine, Br2, and a catalytic amount of phosphorus tribromide, PBr3, followed by water.
How does that work around the enolization problem?
The trick is PBr3 first converts the carboxylic acid into an acid bromide. Acid halides do enolize much more readily than carboxylic acids.
Okay. So it forms the acid bromide that enolizes and gets halogenated at the alpha position.
Exactly. And then the final water step hydrolyzes the acid bromide back to the alpha bromocarboxylic acid. It's a neat workaround.
Very clever. Okay, so that's acid conditions. What about alpha halogenation and base?
Basic conditions lead to something quite different, especially if you have multiple alpha protons. This takes us to the haloform reaction.
Haloform, like chloroform.
Precisely. So under basic conditions, a base pulls off an alpha proton to make the enolate, which then attacks the halogen. Simple enough. But if you have more than one alpha proton on that carbon, it's almost impossible to stop the reaction after adding just one halogen.
Why not?
Because once you add that first electron withdrawing halogen, It makes the remaining alpha protons on that same carbon even more acidic.
Oh, I see. So they get ripped off even faster by the base.
Exactly. So the second halogenation is faster than the first, and the third is faster than the second, if possible.
Yeah.
You get polyhalogenation, usually all alpha protons on one side get replaced.
Okay. So how does that lead to the haloform reaction?
The haloform reaction specifically applies to methyl ketones, compounds with a CH3 group right next to the carbonyl.
Like acetone.
Acetone is the simplest example, yes. If you treat a methyl ketone with excess base and excess halogen, like iodine or bromine, all three protons on that methyl group get replaced by halogens, forming a CX3 group.
Okay, trihalogenated. Then what?
Then, the hydroxide base attacks the carbonyl carbon. Normally, this would just be in equilibrium. But here, the CX3 group is actually a decent leaving group.
Wait, a carbon anion leaving? Isn't that usually a big no-no?
It usually is. Carbon anions are typically terrible leaving groups. But this CX3 anion is an exception. Those three electron-withdrawing halogens stabilize the negative charge on the carbon enough to make it leave.
Wow. Okay, so the CX3 group leaves.
And you form a carboxylic acid, or rather, it's carboxylate salts under the basic conditions. The CX3 anion then gets protonated to form CHX3, the haloform, chloroform, CHCl3, bromoform, CHBr3, or iodoform, CHI3. Iodoform is a yellow solid, so it's sometimes used as a test for methyl ketones.
So the overall result is chopping off the methyl group and turning the methyl ketone into a carboxylic acid.
Exactly. It's a synthetically useful way to do that transformation specifically.
Fascinating stuff. All right, let's switch gears to one of the most fundamental carbon-carbon bond-forming reactions, all reactions.
Absolutely central. In aldol addition, you treat an aldehyde, or sometimes a ketone, with a catalytic amount of base, often hydroxide.
A milder base this time.
Generally, yes, compared to LDA. The base generates a small amount of the enolate. That enolate then acts as a nucleophile and attacks the carbonyl carbon of another molecule of the starting aldehyde or ketone.
Ah, so it reacts with itself.
It does. The result, after protonation, is a molecule that contains both an aldehyde or ketone functional group and an alcohol functional group on the beta carbon relative to the carbonyl,
Beta-hydroxycarbonyl.
which we call an aldol, a portmanteau of aldehyde and alcohol.
Makes sense. What's the mechanism again?
It's usually 3 equilibrium steps. 1. Base removes an alpha proton to form the enolate. 2. The enolate attacks the carbonyl of another aldehyde molecule.
Yep.
3. The resulting alkoxide intermediate gets protonated, usually by water or the conjugate acid of the base, to give the final aldol product.
And you said equilibrium. Does it favor the product?
For simple aldehydes, like acetaldehyde, the equilibrium often does favor the aldol product. But for many ketones, the equilibrium actually lies towards the starting materials. Sterics often play a role. Ketones are bulkier.
So aldol additions aren't always high-yielding for ketones.
Often not. The reverse reaction, called the retroaldol reaction, can be significant, especially for ketones.
Retroaldol, just the reverse process.
Exactly. Base removes the hydroxyl proton, the CC bond breaks, reforming the carbonyl and kicking out an enolate ion as the leaving group.
Another carbon anion leaving group.
Yep. And again, it's allowed because the enolate is resonance stabilized, making it stable enough to depart.
And this isn't just lab chemistry, right? You mentioned muscles earlier.
Absolutely. The retroaldol reaction is biologically crucial. It's a key step in glycolysis, the pathway your body uses to break down glucose for energy.
How so?
An enzyme called aldolase catalyzes a retroaldol reaction on fructose 1-6 bisphosphate, splitting a 6-carbon sugar into 2 3-carbon pieces. This is fundamental to generating ATP for muscle contractions.
So that burst of energy for a sprint, partly powered by retroaldol chemistry.
In a very real sense, yes. It's happening in your cells right now.
Cool. Okay, back to the lab. What happens after the aldol addition? Is that the end of the story?
Often not. If you heat the aldol addition product, especially under acidic or basic conditions, it can undergo dehydration and lose a molecule of water.
Dehydration, forming a double bond.
Exactly. Water is eliminated from the alpha and beta positions, forming a double bond conjugated with the carbonyl group. The product is an unsaturated aldehyde or ketone.
And this whole two-step process addition, then dehydration is called.
That's the aldol condensation. Condensation because water is lost.
What drives the dehydration part?
The main driving force is the formation of that stable conjugated pi system, that extended electron highway we talked about. It provides significant stabilization.
So even if the initial aldol addition equilibrium isn't great, the condensation can pull it forward?
Often, yes. The dehydration can be favorable enough to give good yield to the condensation product, even if the aldol intermediate itself is hard to isolate. And so sterically, the trans or E isomer of a double bond is usually favored.
Okay. Now, what if you try to react two different aldehydes or ketones, both having alpha protons?
That's the challenge of crossed aldol reactions. If both components can form an enolate and both can be attacked, you can potentially get 4 different aldol products, a messy mixture.
Not synthetically useful then. How do you control it?
There are a couple of main strategies. One is to choose one reactant that cannot form an enolate because it has no alpha protons.
Like formaldehyde or benzaldehyde.
Exactly. Formaldehyde, HCHO, or benzaldehyde, PHCHO, are common choices. They can only act as the electrophile, the one being attacked.
Yeah.
So if you react one of these with a ketone or aldehyde that can form an enolate, you generally get only one major crossed product.
Makes sense. Only one component makes the nucleophile.
Right. And particularly with benzaldehyde, the resulting aldol often dehydrates spontaneously to the condensation product because the conjugation extends into the benzene ring, making it very stable.
What's the other strategy for control?
The other way is a directed aldol addition using LDA.
LDA again?
Yep. You take one carbonyl compound, treat it with LDA irreversibly to form its enolate first, get all of it converted. Then you slowly add the second carbonyl compound, which acts as the electrophile. This way you control exactly which enolate forms and what it attacks.
Much cleaner, more control.
Definitely. It's a very powerful technique.
Can these reactions happen within the same molecule?
They certainly can. If you have a molecule with 2 carbonyl groups spaced appropriately, you can get an intramolecular aldol reaction,
Forming a ring.
forming a ring. For example, a 1-thyroid-4-dicarbonyl can form a 5-membered ring, and a 1,005-dicarbonyl can form a 6-membered ring.
And are those ring sizes preferred?
Very much so. Just like in other cyclization reactions, forming stable 5- and 6-membered rings is strongly favored over smaller or larger rings due to ring strain considerations.
Okay, that covers aldols pretty well. Now, what about the Claisen condensation? You said it's the ester version?
That's a good way to think about it. Esters can also react via their enolates in a condensation reaction, analogous to the aldol condensation.
What kind of product do you get?
The product is a beta-keto ester, a molecule with a ketone group at the beta position relative to an ester group.
And what base do you use for this? Can you use hydroxide like in some aldols?
No, you cannot use hydroxide here. Hydroxide would simply hydrolyze the ester back to a carboxylic acid saponification.
Ah, right. So what base then?
You need to use an alkoxide base, and critically, it must match the alkoxy group of the ester.
Match.
So if you have an ethyl ester, you must use sodium ethoxide, NaOA. If you use, say, sodium methoxide, Naomi, you'd get transestrification, swapping the ethyl group for a methyl group competing with the condensation. Using the matching alkoxide avoids this complication.
Okay, matching alkoxide base. How does the mechanism work?
It's similar to the aldol. The alkoxide base removes an alpha proton from one ester molecule to form the ester enolate. This enolate then attacks the carbonyl carbon of a second ester molecule.
Forming a tetrahedral intermediate.
Right. And then, unlike the aldol, where an alkoxide intermediate gets protonated, here the tetrahedral intermediate collapses, kicking out an alkoxide ion as a leaving group to reform a carbonyl. This gives you the beta-keto ester product.
But there's a catch, right? You mentioned something about driving forces for Claisen.
Yes, a crucial point. The overall equilibrium for the steps I just described isn't actually very favorable. What really drives the Claisen condensation to completion is the final step. The beta-keto ester product has alpha protons between the 2 carbonyl groups. These protons are quite acidic, pK around 11, because the resulting enolate is doubly stabilized.
Like the beta-diketones earlier.
Exactly. So the alkoxide base used in the reaction irreversibly deprotonates the beta-keto ester product as it's formed. This final favorable deprotonation step pulls the whole equilibrium over to the product side. It acts like a thermodynamic sink.
So you actually form the enolate of the product.
Yes, which means you need to do a final acid workup step, adding dilute acid, to protonate that enolate and get your neutral beta-keto ester product.
Got it. That final deprotonation is key. And can you do crossed Claisen reactions?
You can, and they face the same selectivity challenges as cross-algyls. If you mix 2 different esters, both with alpha protons, you risk getting a mixture of 4 products.
So similar solutions. Use one ester without alpha protons.
Yep, that's one strategy. Esters like ethyl formate or ethyl benzoate lack alpha protons and can only act as the electrophile. Or again, you could use a directed approach with LDA to form one ester enolate selectively first, then add the second ester.
And intramolecular Claisen, does that work too?
It does. It's called the Dykman cyclization or Dykman condensation. If you have a diester, it can undergo an intramolecular cleavage to form a cyclic beta-keto ester.
And I bet it prefers 5- and 6-membered rings.
You guessed it. Same principle applies. Formation of those stable ring sizes is strongly favored.
Okay, so aldols and clasins build complexity. What about just adding a simple alkyl group to the alpha position?
That's alpha alkylation, a very important transformation. It's typically a two-step process.
Step 1.
Step 1. Form the enolate quantitatively using a strong, non-nucleophilic base like LDA. We want complete conversion to avoid side reactions.
Okay, make the enolate cleanly. Step 2.
Step 2. Add an alkyl halide, RX. The enolate, being nucleophilic at the alpha carbon, attacks the alkyl halide in an SN2 reaction, displacing the halide and forming a new carbon-carbon bond, attaching the R group to the alpha position.
SN2, that means there are restrictions on the alkyl halide, right?
Absolute critical point. The SN2 reaction works best with methyl halides and primary alkyl halides. Secondary halides react slower and often give competing elimination reactions. Tertiary halides basically only give elimination.
Why elimination?
Because the enolate is also a strong base. With hindered secondary or tertiary halides, instead of attacking the carbon substitution, the enolate is more likely to just pull off a proton from the alkyl halide, leading to an alky E2 elimination.
So stick to methyl and primary halides for alpha alkylation via enolates.
Generally, yes, for good yields. And using LDA is beneficial here not just for clean enolate formation, but also because LDA itself is too bulky to easily attack the alkyl halide, further preventing side reactions.
Now, what about those unsymmetrical ketones again, where you could form 2 different enolates? How does that play out in alkylation?
That's where we get into the fascinating concept of kinetic versus thermodynamic control of enolate formation.
Kinetic versus thermodynamic. Explain.
Okay. An unsymmetrical ketone has 2 different sets of alpha protons. Removing a proton from the less hindered side is usually faster, that's the kinetic pathway, leading to the kinetic enolate. Removing a proton from the more substituted side is slower, but leads to a more stable enolate, more substituted double bond character. That's the thermodynamic enolate.
Less hindered, faster, kinetic. More substituted, more stable, thermodynamic. Got it. Can we choose which one we make?
Yes, we can. To favor the kinetic enolate, less substituted, you use a strong, bulky base like LDA at low temperature, typically -78 degrees C.
Why LDA in low temp?
LDA is bulky, so preferentially grabs the more accessible, less hindered proton. The low temperature prevents the kinetic enolate, once formed, from equilibrating to the more stable thermodynamic enolate. It freezes the faster product.
Okay. And to get the thermodynamic one?
To favor the thermodynamic enolate, more substituted, more stable, you use conditions that allow equilibrium to be established. That means a strong but possibly less hindered base like sodium hydride, NaH, and typically room temperature or even slight heating. The reaction can then reach equilibrium, favoring the most stable species.
So you can actually direct the alkyl group to either the more substituted or less substituted alpha carbon just by picking your base and temperature.
Exactly. It gives chemists amazing control over where they build new CC bonds.
That's really powerful. Now, that there are also some classic named syntheses related to alkylation, right? Like the malonic ester synthesis.
Ah, yes, the classics. The malonic ester synthesis is a reliable method for taking an alkyl halide, RX, and converting it into a carboxylic acid with 2 extra carbons, RCH2COOH.
2 extra carbons. Oh.
The key region is diethyl malonate. It's a diester with a CH2 group in between a beta diester. Those alpha protons are very acidic, pK 8-13, because the enolate is doubly stabilized by both ester groups.
So easy to deprotonate.
Yep. You treat diethyl malonate with a base like sodium methoxide, since it's an ethyl ester, to form the enolate. Then you add your alkyl halide, RX methyl, or primary, again, SN2 rules. The enolate attacks the alkyl halide, putting the R group onto that central carbon.
Okay, so now you have R attached to the malonic ester. Then what?
Then you hydrolyze both ester groups to carboxylic acid groups using aqueous acid and heat. This gives you a substituted malonic acid, a molecule with 2 COOH groups attached to the same carbon, one of which also bears the R group.
A 1,3 dicarboxylic acid.
Exactly. And 1,3-dicarboxylic acids have a special property. When you heat them, they readily undergo decarboxylation. One of the carboxyl groups breaks off as CO2 gas.
Leaving just 1 COOH group.
Precisely. Leaving you with RCH2COOH. So you started with RX and you ended with a carboxylic acid that has 2 more carbons, the CH2 and the COOH from the malonate framework.
Very neat. And you could potentially add 2 different R groups.
You absolutely can. You can do the deprotonation alkylation sequence twice, using different alkyl halides each time before the hydrolysis and decarboxylation steps. Very versatile.
Cool. And there's a similar one for making ketones.
Yes, the acetoacetic ester synthesis. It's analogous, but it starts with ethyl acetoacetate, which is a beta-ketoester.
Also has acidic alpha protons between the carbonyls.
Right, pK11. So same sequence. Deprotonate with sodium ethoxide, alkylate with RX, methyl, or primary. This puts the R group on the alpha carbon between the ketone and the ester.
Then hydrolyze and decarboxylate.
Exactly.
Yeah.
Hydrolysis with acid converts the ester to a carboxylic acid, giving you a beta-keto acid.
Ah,
And beta-keto acids, just like one's got their 3 diacids, readily decarboxylate upon heating,
using CO2.
losing CO2, and leaving you with RCH2COCH3, a methyl ketone, where you've installed the RCH2 group. So the synthesis takes RX and converts it into a methyl ketone with 3 extra carbons, the CH2, the CO, and the CH3 from the acetoacetic ester framework.
Why use these elaborate methods instead of just trying to alkylate acetone directly?
Good question. Directly alkylating simple enolates like that from acetone can be messy. You can get over-alkylation, adding more than one R group, self-aldol reactions, and pore control. The malonic ester and acetoacetic ester syntheses provide much more reliable and controlled routes to these specific types of carboxylic acids and methyl ketones.
They avoid the pitfalls of direct alkylation. Makes sense.
Exactly. They use the enhanced acidity of the beta-carbonyl starting materials to ensure clean enolate formation and alkylation.
All right, let's shift focus slightly to conjugate addition reactions, the beta attack.
Right. This involves those base-unsaturated aldehydes and ketones we formed earlier via aldol condensation. We often call them enones or enols.
And they're special because they have 2 electrophilic sites.
Precisely. Due to resonance, not only is the carbonyl carbon electrophilic, like in any ketone-aldehyde, but the beta-carbon is also electron deficient, making it electrophilic too.
So nucleophiles have a choice. Attack the carbonyl carbon position 2 or the beta carbon position 4.
Exactly. Attack of the carbonyl carbon is called 1,4 addition. Attack of the beta-carbon is called 1,4,4 sortie addition, or, more commonly, conjugate addition.
And what determines where the attack happens?
It often depends on the type of nucleophile. Very reactive, hard nucleophiles like Grignard reagents, RMGX, or organolithiums, RLI, tend to favor 1,4,2 addition direct attack at the carbonyl.
Okay. And conjugate addition.
Less reactive, softer nucleophiles tend to favor 1/4 conjugate addition. A prime example is lithium dialkyl cuprates, R2CLI, also known as Gilman reagents. They almost exclusively add to the beta position.
Cuprates for 1,4,4 addition. Got it. Where does the Michael reaction fit in?
The Michael reaction is a specific type of conjugate addition where the nucleophile is a relatively stable, weakly basic enolate, typically one that's doubly stabilized.
Like the enolates from malonic ester or acetoacetic ester?
Exactly. Those enolates, along with enolates from beta-ditones, beta-ketonitriles, nitroalkanes, these are called Michael donors. They're soft nucleophiles and react reliably via 1/4 addition with unsaturated carbonyl compounds, which we call Michael acceptors.
So Michael reaction, doubly stabilized enolate, adding 1 more 4 to an enonyl.
That's the core idea, yes. It's a very powerful way to form CC bonds further down the chain from the carbonyl.
And you mentioned this connects to biology again. Detoxification.
It absolutely does.
Yeah.
Michael addition is a key reaction in biological detoxification pathways. Your body contains a molecule called glutathione, which is a tripeptide with a very nucleophilic thiol DSH group.
Okay.
Harmful electrophiles, including some drug metabolites or environmental toxins that have Michael acceptor structures, can react with glutathione via Michael addition.
So glutathione adds to the harmful molecule.
Yes, tagging it for excretion and preventing it from reacting with crucial biomolecules like DNA or proteins. It's a major defense mechanism.
And this relates to acetaminophen overdose.
It does. A toxic metabolite of acetaminophen, paracetamol, is a Michael acceptor. Normally, glutathione handles it, but in an overdose, glutathione supplies get depleted. The toxic metabolite then reacts with liver proteins, causing severe damage. That's why overdose is so dangerous. It overwhelms this Michael addition detox pathway.
Wow. Okay, vital chemistry. Now, what if you want to do a conjugate addition, but your nucleophile is just a regular ketone enolate, not one of those doubly stabilized Michael donors?
Good question. Regular ketone enolates are generally too reactive and too basic. They tend to do 1-2 addition or just act as bases rather than undergoing clean 1-4 Michael addition.
So another workaround needed.
Yep, and the clever workaround here is the Stork-enamine synthesis.
Enanamines. What are those?
You form an enamine by reacting a ketone, or aldehyde, with a secondary amine, R2NH, under slightly acidic conditions, removing water. An enamine has a C-Fe double bond adjacent to a nitrogen atom.
Okay, CECNS, how does that help?
Enamines are electronically similar to enols and enolates. They have resonance structures showing that the alpha carbon is nucleophilic. But crucially, enamines are less reactive than enolates because they are neutral molecules, not anions. They don't carry that strong negative charge.
Ah, less reactive. So they're softer nucleophiles.
Exactly. This reduced reactivity makes them perfect candidates for acting as Michael donors in conjugate additions. They add cleanly 1,4 to Michael acceptors, where a simple enolate might fail.
So the Stork synthesis. Make the enamine from your ketone, react that with the Michael acceptor, 1,4,4 addition, and then what?
Then you just add water and acid, hydrolysis, to convert the intermediate back into a carbonyl group. So the net result is the conjugate addition of your ketone's alpha position to the Michael acceptor. Brilliant strategy.
Very clever indeed. Okay, one more big one. The Robinson annulation. Sounds impressive.
It is impressive. Annulation means ring forming. The Robinson annulation is a powerful sequence that combines two reactions we've already discussed to build a six-membered ring onto an existing molecule.
Which two reactions?
It's a Michael addition followed immediately by an intramolecular aldol condensation.
Wow, putting it all together.
Exactly. Typically, you react a ketone enolate, often formed under conditions allowing Michael addition, maybe using an enamine, with an unsaturated ketone, like methylvinyl ketone, MVK. The Michael addition happens first, connecting the two molecules.
Creating a 1,3,5 dicarbonyl compound.
Precisely. And that 1,3,5 dicarbonyl compound is perfectly set up to undergo an intramolecular Aldol condensation, base-catalyzed, often just using the same conditions, to form a new six-membered ring containing an unsaturated ketone.
A cyclohexanone ring.
Yep. It's a cornerstone reaction for synthesizing polycyclic compounds, especially steroids and terpenes found in nature. Really a workhorse reaction.
Okay, that's a lot of reactions. How do we start putting this together strategically? Let's talk synthesis strategies.
Right. When you're faced with synthesizing a target molecule, especially one with multiple functional groups, you need to think retrosynthetically, work backwards.
Yeah.
Look at the function groups and their relative positions.
The relationship between them tells you which reaction might have formed them.
Often, yes. Here's a key takeaway based on the relative positions and numbering pattern.
Okay.
If your target molecule has functional groups in a 1005 relationship, like a 1005 ditone, or something derived from that, you should immediately think Michael addition, or maybe Stork enamine synthesis. Those reactions create that 1005 pattern.
1005 means Michael or Stork. Got it. What about 1,3?
If your target has functional groups in a 1,4-3 relationship, like a beta-hydroxy carbonyl and a β-unsaturated carbonyl, a beta-keto ester, or a 1,4-3 ditone, then you should be thinking aldol addition condensation or Claisen condensation.
143 means aldol or Claisen. How do you pick between aldol and Claisen if it's 143?
Look closely at the oxidation states of the two functional groups. Aldol reactions typically connect a carbonyl to what becomes, or started as, an alcohol. Claisen reactions connect two carbonyl-level functional groups, like a ketone and an ester. That difference often points you to the right disconnection.
That's a really useful way to think backwards. Look at the 1,3 or 1,4,5 pattern.
It's a very powerful heuristic for planning syntheses involving these types of compounds. It helps you choose the right tool from the toolkit we've just discussed.
And can we combine some of these ideas, like Michael addition and alkylation?
Absolutely. Remember that the immediate product of a Michael addition after the 1,1-a-few attack is actually an enolate ion.
Ah, right, before it gets protonated.
Exactly. So instead of just quenching that enolate with water or acid, you can trap it in situ with an alkyl halide.
So you do a Michael addition to add a group at the beta position and then immediately alkylate the resulting enolate at the alpha position.
Precisely. It's called tandem Michael addition alkylation. It allows you to install one group at the beta carbon and a second group, potentially different, at the alpha carbon, all in one pot. Incredible efficiency and control.
Wow. So putting it all together, these alpha-carbon reactions, they really give you fine control over building molecules.
Immense control. From simple alkylations to forming rings with Aldol or Robinson to the strategic placement using kinetic thermodynamic enolates or conjugate addition. It's the foundation of much of modern organic synthesis. Understanding anols and enolates unlocks the ability to build complex structures with precision.
So what does this all mean for you, the listener? It means mastering these fundamental reactions: alpha carbon chemistry, enols, enolates, halogenation, Aldol, Claisen, Michael, Stork-Robinson gives you this incredible versatility. You can build complex molecules, strategically place multiple carbon chains, and really understand how chemists construct the molecular world.
And thank you for diving deep with us today. We've journeyed through this dynamic world of alpha carbon chemistry, uncovering how these really clever reactions let chemists build intricate structures from small chains to complex rings. We've hopefully clarified key concepts and problem-solving techniques.
And what's truly amazing, as we saw, is how these very same chemical principles are humming away inside your own body right now, powering your muscles through glycolysis, detoxifying things with glutathione. It's fundamental chemistry at work.
We really hope this deep dive helps you unlock new understanding and appreciate the intricate dance of molecules all around us and within us, sparking maybe even more curiosity.
And thank you, as always, for being part of our last-minute lecture family.